Hello my dear students, welcome to ICS Mahesh PU College, Dharwad. In this session, we are learning another important topic of electrochemistry, limiting molar conductivity. So we have seen what is molar conductivity and all in the last session. We are going for limiting molar conductivity today. Myself Jayraj Agade, let us go for the topic without any delay. In the previous video we have learnt 2 points. One is the conductivity and molar conductivity, how it varies with dilution. As we already know, the conductivity decreases with dilution, conductivity or a specific conductance decreases with dilution, and molar conductivity increases with dilution. We have seen the graph for weak electrolytes and strong electrolytes already in the last session. So this is what the graph is. For strong electrolyte, if we decrease the concentration, the molar conductivity increases. Similarly, for weak electrolyte, if we decrease the concentration, molar conductivity increases, but in an exponential way if we decrease the concentration. These things we have already learned in the last session. Let us go for another point, limiting molar conductivity or molar conductivity at infinite dilution. We even call it as molar conductivity at zero concentration. All are same. Limiting molar conductivity at infinite dilution, or molar conductivity at zero concentration, all are one and the same. Let us see what it is exactly. When a concentration of solution approaches to zero, if we are calculating a molar conductivity for 1 mole of electrolyte we have taken, and we start measuring its molar conductivity, the value what it approaches, we will get different values. If we decrease a concentration, molar conductivity increases. But the value of molar conductivity when the concentration is almost approaches to zero. Theoretically, we say it is almost equal to zero. Practically, it is impossible. Theoretically, when the concentration is almost approaches to zero, whatever the value of conductivity we get, we call it as limiting molar conductivity or molar conductivity at infinite dilution. See, if we want to give an example or analogy, if we add a small amount of salt to an entire lake, the concentration of the salt in the lake is almost negligible. That's what we can call it as when the concentration approaches to zero. So that's how we can actually determine molar conductivity, not by measuring, but actually we calculate it using graphical method or Coriolis law. Let us discuss it later. Let us take an example. For a strong electrolyte, lambda m is related to lambda m naught by this equation. See, this equation we call it as Debye-Huckel-Onsager equation. In the last session, probably you have seen, we have taken the graph of lambda m versus root c. We have not taken lambda m versus c, we have taken lambda m versus root c. That is because of Debye-Huckel-Onsager equation. Debye-Huckel-Onsager equation says lambda m is equal to lambda m naught. This lambda m naught is called as limiting molar conductance, limiting molar conductivity, and C is the concentration, and lambda m is the molar conductivity at a concentration C. Here A is a constant. This equation we call it as Debye-Huckel-Onsager equation. Here I have discussed the points, what is lambda m, what is lambda m naught, and what is A. A is a proportionality constant. With that we'll discuss it what is exactly later. If we plot lambda m versus root c, versus root c, because that is in the lambda m is equal to lambda m naught minus a into root c, that is in the form of y equal to mx plus c for strong electrolyte. So that's why it appears to be straight line. This is a straight line. Lambda m versus root c will be straight line. What if I extrapolate this, and where it touches this y-axis, we call it as lambda m naught. And whatever the slope of this straight line is minus a, as the minus sign, because it is the negative slope, and the slope will be minus a. See, what does that a value depends on? This a value depends on many factors like viscosity of the solution, or temperature of the solution, or the charge on the individual ions present in the electrolyte. If for a particular solution containing same viscosity and same temperature, if they have same pair of charges, they must have to have same value of A. See, NaCl, Na plus, Cl minus, K plus, Br minus. This is 1:1 electrolyte. So that's why these two should have same value of A for a same solution. Similarly, MgCl2 and CaCl2, Mg2 plus, Ca2 plus, Cl minus, Cl minus, MgSO4, CaSO4. Here the charges on the individual ions are same. This is 2:2 electrolyte. This is 2:1 electrolyte. If it is having same charges on the ions, cations and anions, they must have to have same value of A. How to calculate it for weak electrolyte? See, this is a line of weak electrolyte. This is for strong electrolyte. We can calculate for strong electrolyte. Lambda m naught can be calculated. The limiting molar conductance can be calculated by extrapolating the graph where it touches y-axis, which is I already told. But how to calculate it for weak electrolyte? We cannot exactly calculate for weak electrolyte because it never touches y-axis. See, here the molar conductivity of weak electrolyte abruptly increases with increase in the dissociation of ions. So if I decrease the concentration, it will not be a straight line, it will be an exponential line. So that's why it never touches y-axis. That is the reason by graphical method I cannot determine the limiting molar conductance of weak electrolyte. Limiting molar conductivity of weak electrolyte can be determined by Correla's law. We can discuss it in the next class. Thank you for today. Please support, share, like and subscribe. Thank you.